start today's class. Last two classes we have been talking about advanced aluminum alloys. There is a little more in that direction we will continue today, and then go into the titanium based alloys. So among all the alloys that we talked about, aluminum based alloys, we talked about amorphous aluminum based alloys, nanocrystalline aluminum based alloys, nano quasi-crystalline aluminum based alloys, and nano composites. There are a few more nano composites which I thought literature is available, so I thought I would give you some more examples of that. One such thing is aluminum iron based alloys. As I told you before, people want to put into aluminum all kinds of high temperature materials, high temperature, high melting metals. One such example you have already seen is titanium. So why do we put this? This is basically to improve the high temperature strength of aluminum, because when you put elements which have high melting points, then these elements, their diffusivity is going to be low at the temperature of the use, and because of that the creep is going to be much more difficult in those alloys. So whenever you add to aluminum, we know is a very low melting metal, 660. So as a result its creep resistance is very poor. So creep is related to diffusion. So we all know, and grain boundary sliding. So everything is related to high temperature, deformation is related to diffusion. So as a result, if you can somehow constrain the diffusion or slow down the diffusion process, we can increase the creep life of any alloy. So in that direction people try to put a number of elements. For example, iron is one, titanium is another, vanadium. For example, aluminum, iron, vanadium, silicon alloys is very popular alloys for high temperature applications, where people try to put iron, vanadium, silicon and try to get a two-phase microstructures which can give you much higher strength. So here is one such example, aluminum iron, where different amounts of iron are added to the aluminum, 2.5%, 5%, 10%, 15, 20%. And you know, as I told you, the most important compound in all these alloys is what? The Al3Fe, Al3Ti, this type of a phase. The reason is, as I told you, it's a high melting compound. In addition, it has large amount of aluminum in it, and because of which its density is lower. So as a result, if we can have a Al3 plus metal type of a compound, Al3Ti, Al3Ni, Al3Fe, this kind of compounds, these are all aluminides. If you can have that kind of a compound as a precipitate in an aluminum matrix, one can achieve much higher strengths. So keeping that in the mind, so people do not add too much of an alloying elements into it, those alloying elements which can give you Al3Fe. Okay, so that is the composition ranges people work on. So that's why we are still below the 25% of iron into it. So if you add these different alloying elements, and this the technique that people have used here is mechanical alloying. As I told you, all these nano composites can be produced by basically two techniques. One is the rapid solidification processing, another is mechanical alloying. So this particular example is for what is called the mechanical alloying. And if we look at the XRD patterns, what you basically see that after 20 hours of mechanical alloying of aluminum plus iron, of different amounts of iron into it, you will basically see only aluminum peaks, suggesting that it is the iron which has dissolved into aluminum, and what you have is basically a solid solution. But one interesting thing that you look at this more carefully, you will see that the aluminum peak, the first peak which is around 45 degrees which you see here, is the aluminum 111 peak here. This peak which you see here as aluminum 111 peak, its intensity keeps on decreasing as you increase the iron. And the second peak here which you see is the aluminum 200 peak. That intensity with respect to the aluminum 111 intensity is increasing. So initially at 2.5% you have the 111 peak which is more intense than the 200 peak, which is what we expect for a pure aluminum. When you take a pure aluminum and do X-ray, always in an FCC metal, 111 peak has the highest intensity than the 200 peak. Is it always true? Do we have any exceptions? Usually, whenever you take a metal, mostly pure metals, you will see that the first peak is the most intense peak and the other peaks are lower intensity. But there are conditions where it is possible for the second peak or the third peak being more intense than the first peak. When do you observe such a situation? No? Preferred orientation, that's it. Texture. If you have a texture, let's say you take iron and keep rolling it in a particular direction, let's say 200 direction. Once you do that, all grains are oriented in a 200 direction, and take that and do an X-ray, you will not see 110 peak there. Iron is BCC, so 110 is supposed to be the most intense there. So 110 will have a lower intensity than the 200. So unless you have a preferred orientation, if you have a random orientation, usually the first peak is the most intense peak, and that's what you see here. And when you do mechanical alloying, which is a ball milling process where the balls are hitting the powder, there is no chance of a preferred orientation coming into picture, because these are all random collisions of, so it is not possible for the grains to be elongated in a particular direction. That kind of a chance does not exist. So the possibility of second peak becoming more intense than the first peak does not arise because of the texture in this kind of material. So what is the possible reason why the second peak is becoming more intense than the first peak? That basically means some other phase is coming out. Unfortunately, that second phase which is coming out overlaps with the first peak. If you carefully observe the 20 iron, you can see some kind of a shoulder on the left side, and that shoulder indicates that there is another phase which is Al5Fe2. This is interesting to note, that the composition is very close to Al3Fe. Under equilibrium conditions, the phase that you are supposed to expect is the Al3Fe, but you don't get Al3Fe, but you get another phase called Al5Fe2, because Al5Fe2 is a higher melting metastable phase which can easily nucleate in an aluminum matrix than the Al3Fe. That's why these are some metastable phases which always come out. Probably if you take this alloy and then heat treat it at high temperature for a long period, again you get back to the equilibrium conditions. So this is what you see here, and to identify that, if you take the aluminum 111 peak and the iron 110 peak and take the ratio of these two and plot it as a function of time or plot it as a function of composition, you will see that at 25% this should go to 0. Why? At 25%, the aluminum 111 versus iron 110, if you take it, that ratio will go to 0 there. The reason is that 25% composition is equivalent to the Al3Fe composition. So if you choose the Al3Fe composition and make an alloy of that composition, at that composition you will not have any aluminum, you will have a single phase intermetallic compound in a phase diagram. This is nothing but like a lever rule. The volume fraction of the aluminum keeps on decreasing as you keep on going towards the Al3Fe, and once you reach the Al3Fe composition, then there is no aluminum, it is only Al3Fe. So that's what you see here. As you keep on plotting this ratio, aluminum keeps on decreasing, and that's what you see here in the X-ray also. The aluminum peak keeps on decreasing, and when you go to 25%, it will completely vanish. There will be no aluminum, it will be only single phase intermetallic compound. So one can produce this kind of phases which are nanocrystalline in nature by mechanical alloying. And look at the lattice parameters. As I told you before, one can calculate the lattice parameters based on, how do you calculate the lattice parameter of various alloys? using an X-ray diffraction? Yes, just simply from the Bragg's law and the relation between d-spacing and the lattice parameter, one can do it. And if you look at the previous one, you can see that the peak which you have, aluminum peak, keeps on shifting. Aluminum peak and the position, if you look at it, the aluminum peak position at 2.5% is different from at 20%. So this clearly tells you that there is some solubility of iron into aluminum, and because of which the peaks are shifting. And from the peak shifts, one can calculate what is the solubilities also. So when you plot the lattice parameter, what you see is that lattice parameter does not change much up to about 10%, and from there, in fact, there is a decrease in the lattice parameter, as marginal decrease in the lattice parameter as you increase the iron content up to 10%, because iron is slightly smaller atom than the aluminum. So when iron goes into aluminum, the lattice parameter decreases, or the overall atomic radius decreases. So as a result, you can see a small decrease, and but later than this 10%, you see suddenly there is an increase, and this increase is coming because of the formation of the second phase, the Al3Fe. So which overlaps with that peak, and because of which one can find out that the peak sudden increase in the lattice parameter is because of the formation of Al5Fe2. So one can do this kind of lattice parameter calculations and also correlate the crystallite size to the lattice parameter. You can see as you keep on doing ball milling, the crystallite size decreases, and once the crystallite size comes to about 20 nanometers or so, suddenly the lattice parameter starts changing. Up to that time, there is no change in the lattice parameter much. This is what I told you long back also. Nanocrystallization is a prerequisite for alloying during mechanical alloying. Unless it becomes nanocrystal, it cannot become an alloy. So nanocrystal formation is crucial for the alloy to form, for one element to start diffusing into the other, because this diffusion is occurring at room temperature, isn't it? Whereas if you make this alloy by normal conventional liquid metallurgy route, you are making the alloy at high temperature where the diffusion can easily occur. So here you want the diffusion to occur at room temperature. How can the diffusion occur at room temperature where it has a large activation barrier? So it can occur only when you bring down the diffusional distances. So if you can bring down the diffusion distance, the gradient becomes very large, extremely large, because what you see dc by dx becomes very large when the dx becomes very small. And that's what you see, that even if the temperature is very low, the diffusion can occur at room temperature because of the small crystallite size that you have. If the crystallite size becomes very small, then the diffusion can occur very easily. And also at those small crystallite sizes, the defects are so much inside the material that diffusion can occur very easily. And the surface of these nanocrystals being random in nature, so a lot of solute can dissolve into the surface of this. That's why we have seen earlier also that the grain boundary volume, as it increases, the solubility increases. So that's what you see in the nanometer, and all this occurs below a certain crystallite size. So we have to reach around 20 to 25 nanometers for the lattice parameters to start increasing. Okay, and people have also tried to look at what are the strength levels of these nanocomposites, and here what you see is nothing but the hardness, the Vickers hardness of these nanocrystals, nanocomposites as a function of composition. You can see as the composition is increasing, the hardness is increasing, and the hardness reaches almost about 2 gigapascals, and which is much higher when compared to the hardness of most of the normal aluminum alloys. Normal aluminum alloys, you get hardness of the order of around, in terms of Vickers hardness, if you look at it, around 60-70 Vickers hardness. You do not get much beyond that. So here you get around 200 Vickers hardness, which is equivalent to about 2 gigapascals. And the densities of these alloys, green densities without any sintering, one can achieve about 85% or so. 75 to 85% of green density one can achieve in these nanocrystals. This is one of the advantages of nanocrystalline materials, people say. Usually by normal powder metallurgy route, you have the problem that achieving high densities is very difficult. You need to go to very high temperatures of sintering in a normal powder metallurgy. I think some of you are taking powder metallurgy course. So you know that compaction and sintering at high temperatures is crucial, and many times people do what is called liquid phase sintering, that one of the phases present in the material melts and provides the required bonding that is required for getting high dense compacts. Whereas in a nanocrystalline material can flow more easily, and you have large grain boundaries available and for achieving high densities, and that's why this you can, even at normal green compaction, you can achieve almost 85%. In a number of composites, people have achieved even 90-95% just by green compaction. So one can achieve high densities in these materials. Another possibility in these is to produce intermetallics. We have talked about so far composites, nanocomposites. One can also make nanocrystalline single phase intermetallics, which can be useful for high temperature applications when people want to look for high strengths at high temperature. But at the same time, you may say, how do we use nanomaterials at high temperature? Because nanomaterials usually grow at high temperatures. So one has to consider how to control the growth of these nanograins. The grain coarsening has to be controlled. So if one can control the grain coarsening, one can definitely achieve high strengths at high temperatures in these intermetallics. And these intermetallics, one more important point that you have to note down is that it is very difficult to make them by normal conventional route, because I told you most of these intermetallics have very limited composition ranges, and one of the element has much lower melting point, aluminum, the other element has much higher melting point. So when you try to melt them together, before one of the element starts melting, you may start seeing some evaporation of the second element, and because of which you lose lot of element. So one has to consider these losses and add additional excess element of aluminum so that you can maintain this composition. So maintaining the composition is very crucial in this kind of melting practice, where one of the element has much higher melting point than the other. So when the melting point difference between the two is largely different, it is very difficult to use liquid metallurgy route to make alloys, and that's where this kind of mechanical alloying becomes very useful, where you can take the two elements and mix them together and do ball milling and produce nanocrystalline intermetallics such as nickel aluminide shown here over wide composition ranges. For example, NiAl you can make only from 45 to 55 composition range percentage nickel in the equilibrium phase diagram, whereas one can produce from 25% to 65% if he goes by this kind of non-equilibrium processing routes, whether it is rapid solidification or mechanical alloying. Mechanical alloying definitely gives you much wider composition ranges. And similarly, Al3Ni, which is a line compound here, can be made over a range of composition again by this mechanical alloying process. So one can make these things over wide composition ranges in a nanocrystalline form, as you can see here, very fine grain sizes, and one can use them for any application of interest. Other intermetallics that can also be produced is the Al3Ti, Al3Zr, particularly the L12 type of compounds. As I told you before, Al3Ti and Al3Zr usually exist in the body centered tetragonal form, BCT type of compounds, and BCT type of compounds are more brittle. So as a result, people wanted to make the cubic type of compounds by modifying the structure from the tetragonal to the cubic form, and to do that people have done a lot of process. One is what I told you before, probably rapid solidification processing, where you can suppress the BCT to nucleate, and so that the FCC can easily nucleate. FCC is a simpler structure which can nucleate much more easily. Other possibility is to add certain alloying elements which can stabilize the FCC structure rather than the BCT type of structure, such as chromium, manganese, copper, nickel. A number of these elements have a tendency to stabilize the L12 phase. So that is one possibility. Another possibility is to go through a process such as mechanical alloying. where one can easily produce these compounds. So I told you in mechanical alloying, the phases that come out are always those with lower interfacial energies. So, and high symmetry element structures such as the cubic structures. High symmetry structures always have much lower interfacial energies. So cubic structure can form much more easily. So you can see here that if I take aluminum, titanium, zirconium type of a ternary mixture, 75% aluminum, 25 minus X and zirconium X. So keep on varying the amount of zirconium. So when zirconium is 0, it is Al3Ti. When the zirconium is 25, it is Al3Zr. So you are changing the composition in such a way that you have all these ternary compound, and in all the cases you get the L12 phase after a certain time of milling. This is 20 hours, and here we show you that lattice parameter, how does it change as a function of time for different compositions. You can see that if the composition is less than about 15%, the lattice parameter decreases. That means when titanium goes into aluminum, when the percentage zirconium is less than 10, that means you are basically on the Al3Ti side, isn't it? Zirconium is low, titanium is more. So when the titanium is more and zirconium is low, you are on the Al3Ti side of the phase diagram. So if you are on the Al3Ti side, you will see the effect of titanium here into that. So as the titanium goes into the aluminum, the lattice parameter decreases, and beyond a certain time it stabilizes, and that is where the Al3Ti forms. So after about 15 hours of milling, Al3Ti forms and the lattice parameter gets stabilized. And if you use higher amount of zirconium, you see zirconium is a much bigger atom, and when a bigger atom goes into aluminum, then you will see that the lattice parameter increases, and that's what you see here. And when you add some combination, a proper combination of titanium and zirconium, the lattice parameter does not change much at all. And this lattice parameter is what? The starting lattice parameter is the lattice parameter of aluminum we are talking about. So that means the intermetallic compound that you are making has exactly the same lattice parameter as that of the aluminum. And this is very crucial when you want to make nanocomposites. If you want to make a nanocomposite of aluminum and Al3Zr or Al3Ti, if you can take a proper combination of titanium and zirconium and make a Al3Ti-Zr kind of L12 compound, now you have an FCC compound in an FCC matrix whose lattice parameters are exactly similar. So you have a matrix whose lattice parameter is same as that of the intermetallic compound, and if you have that kind of a situation, you have perfect coherent precipitates possible. Because as I told you, when you want to have coherent or semi-coherent precipitates, what you need is that the misfit should be as small as possible. The lattice parameter difference between the matrix and the precipitate should be minimized, and if that is small, then you can have what are called the coherent precipitates or semi-coherent precipitates. And this is one way to engineer or tailor the lattice parameter of the compound such that the lattice parameter of the compound becomes close to that of the lattice parameter of the matrix. So with this kind of possibility, people have been able to make nano composites with different amounts of titanium and zirconium into it, so that one can make a Al3Zr Ti kind of ternary compound, which is a cubic structure in an aluminum matrix, which has again a cubic structure. The only difference is one is ordered cubic, another is a disordered cubic. That's the only difference. And these are all in the nanocrystalline form. One can easily see very fine crystals of the order of around 10 to 20 nanometers. This is a dark field image in a electron microscope, and you can see these rings. The sharp rings clearly indicate that it is a nanocrystalline. So you can see that in a electron diffraction, always whenever you get a sharp ring, it means it's a nanocrystalline. So from this one can calculate the lattice parameters from the diameter of the rings and the d spacings first, and from d spacings one can calculate the lattice parameters. And it is also important to note that the crystallite size of this compound also decreases with increasing mechanical alloying time, and once you reach about 20 hours, you have about 15 nanometers or so. So the crystallite size is again a function of the time of milling, and it's also a function of the percentage of zirconium in it. So the higher the amount of zirconium, you get a lower crystallite size. And what is also important is that the formation of these compounds again occurs below a certain crystallite size. If you plot the crystallite size as a function of the composition of zirconium, with different amounts of zirconium, try to look at what time the intermetallic is forming, and look at the crystallite size at each of those times. This is all, for example, different symbols here show you different crystallite sizes at different ball milling time. And if you look at that, once you reach below 20 nanometers, that is the time at which the formation of intermetallics occurs. So below about 20 nanometers, the ordered compounds form. So as we have seen before also, in case of NiAl also, or Al3Ni also, we have seen that below a certain crystallite size the compounds form. Exactly similarly here also, below a certain crystallite size all the compounds form. And this is again the lattice parameter and crystallite size. Crystallite size after 20 hours of milling is more or less constant in all the compositions. You can reach almost about 15 nanometers. You can see on the right side crystallite size is plotted. So the crystallite size is more or less constant, and the lattice parameter keeps on increasing as a function of composition. And zirconium rich compositions have high lattice parameters, zirconium poor compositions have low lattice parameter, and somewhere in the middle the lattice parameter is very close to that of the pure aluminum lattice parameter. Okay. And this is again showing the lattice parameter as a function of composition, and the LRO, this is another important parameter, what is called long range order parameter. So how ordered the compound is. So the order parameter of the compound keeps on increasing with the amount of zirconium. So zirconium rich compounds are more ordered than the titanium rich compounds, because titanium Al3Ta has a lower ordering energy than Al3Zr. So as a result, Al3Ta can become more easily disordered when compared to Al3Zr. So Al3Zr is one point you have to always remember is that these are all in the mechanically alloyed condition. When you mechanically alloy, you are always introducing a lot of defects into the system. When you are introducing defects into the system, the order parameter cannot become equal to 1. Order parameter of 1 means what? It is completely ordered. Order parameter of 0 means it is completely disordered. So from this you can see that even with single phase Al3Zr with 25% zirconium in it, the order parameter is only 0.6. That means it is only 60% ordered. 40% disorder is still there inside it. And where is this 40% disorder coming from? It is coming from the defects that you are putting into the crystal because of the high intensity ball milling that you are putting in, and because of that a lot of defects are generated. But what is important is under the same milling conditions, the Al3Ta has much lower order parameter. It is only 0.1 or so, whereas with Al3Zr composition it is 0.6. So you can from that one can easily see that Al3Ta becomes disordered much more easily than Al3Zr. This is again related to the thermodynamics, that the ordering energy of Al3Ta is much lower than the ordering energy for Al3Zr. And with this we will stop as far as aluminum alloys are concerned, and now let us go into the titanium based alloys. Titanium based alloys have been quite popular in recent years, particularly as an alternative to aluminum based alloys. Why? Because titanium is also a low density metal similar to aluminum, not as low density as aluminum. What is the density of titanium? Anybody knows? It's 4.5. What is the density of aluminum? 2.7. So at least aluminum you know. So aluminum is 2.7 and magnesium is much lower. So magnesium alloys are much more attractive, but there are problems. Why? Corrosion problem, and most important thing is the structure. Look at the structure of magnesium and look at the structure of aluminum. Aluminum is FCC, magnesium is HCP. HCP metals are not easily formable like FCC metals. So that's why if you want to use a magnesium based alloy, so its formability is much lower than because the number of slip systems are much lower, we all know this. So as a result, magnesium alloys will not have easy formability. And also magnesium has a lower melting point than titanium, than aluminum, sorry. So because it has a lower melting point than aluminum, so its creep resistance is also lower than aluminum. So as a result, you cannot use magnesium alloy to high temperatures. Aluminum also we cannot use, but the temperature capability of magnesium is definitely lower than that of the aluminum because the melting point itself is lower. So there are two disadvantages particularly with magnesium alloys. One is the low melting point, second is the structure being HCP, and the third point which Ravindra has pointed out, the corrosion problem and its reactivity. Magnesium is much more reactive. In fact, melting and casting of magnesium alloys is much more difficult than aluminum. Aluminum can be easily melted and casted because magnesium catches fire very easily. So you cannot melt and cast so easily. For example, Muthu is struggling to make magnesium based alloys. So you know that magnesium based alloys are not very easy. So that's why people started looking for other alternatives to aluminum. And definitely it's very difficult to find out metals which are much lower density than magnesium aluminum. So people started looking for slightly higher density, at the same time strong alloys and useful alloys. That's where titanium comes into picture. Titanium has a density of about 4.5, and so obviously it's almost somewhere in the middle between aluminum alloys and steels. Steels, what is the approximate density? Iron. So 7.8 is for iron. So most of the steels, depending on the alloying elements, it changes of course. So around 7.5 to 8, let's say, is the density of steels. One can take it, and so this is titanium is somewhere in the middle. So density wise it has an advantage. It has good corrosion resistance. Its melting point is very high. What is the melting point of titanium? Is 1668 to be exact. So 1668 is much higher than even iron. Iron is 1535. So it has a higher melting point than iron. So definitely it's very attractive. And more important thing is that it has an allotropic transition. If you look at here, titanium has an allotropic transition from alpha to beta at about 882 degrees centigrade. The low temperature form is called alpha. What is the structure of that? It is HCP. Alpha is HCP. So titanium at room temperature is HCP, and titanium at high temperature beyond 882 is BCC, beta. So once you have an allotropic transition, there is a lot of advantage, and that's the basic advantage of steels. Why steels have become so popular among all the alloys is just because of these allotropic transitions. The moment you have an allotropic transition, you can heat treat it. If you don't have an allotropic transition, aluminum, pure copper, you cannot do any heat treatment. So the strengthening is limited in metals without any allotropic transition. Aluminum can be strengthened only by putting some precipitates into it. You can do some what is called solid solution strengthening. You can do what is called strain hardening. Nothing beyond that. And the amount of strengthening that you can achieve by both solid solution strengthening and strain hardening is not very high. And precipitation hardening, that's why is one of the routes people use. And so if one can heat treat the alloy and produce different morphologies of the second phase, one can have much higher strengthening possibilities. So that's where the titanium alloys are similar to aluminum alloys. That's why people similar to iron based alloys. That's why people call titanium as the iron of non-ferrous metals, because it's almost like iron. That whatever you can do, for example, you can have perlite in titanium based alloys, you can have binite type of structures, you can have even martensite. Take the high temperature BCC alloy, quench it, you have a martensite, and take the martensite, start tempering it, you can have all kind of tempered structures whatever you generate in steels. So similarly, you can have the second phase with different sizes. Okay, one can vary the size of the precipitates sizes by controlling the cooling rate, annealing, normalizing, all kinds of things that you can do with steels. Exactly, you can do with titanium-based alloys. So that's why titanium-based alloys have become very popular. But there are limitations with both alpha and beta. What are the limitations of alpha? Formability is the limitation because it is hexagonal structure. So as a result, one cannot use it for highly formable type of structures. If you want to use titanium based alloys, what are the basic applications of these titanium based alloys? One is jet engines. People want to use them for high temperature jet engines. Second is for the frame, airframe. So if you want to use it for airframe and jet engine, the requirements are different. For jet engine, what you need is a high temperature strength. For airframe, what you need is a good formability, because you have to make them into sheets, isn't it? So definitely, so one has to think of which one to be used where. So the alpha is a structure which is hexagonal. So hexagonal structure, diffusivity is much more difficult than a BCC structure. BCC is a more open structure, so diffusion can occur more easily. So definitely we cannot use BCC structures for high temperature applications. That's why all superalloys, you look at all the superalloys, nickel based superalloys, iron based superalloys, nobody will use an alpha iron for a superalloy. People will always use a gamma iron because that's a FCC structure. Similarly, the cobalt also. For cobalt based superalloys, when we come to superalloys, we will talk about those things. Cobalt also has a phase transition. So we use all those structures which are more close packed structures for high temperature applications. So alpha is one such example. So if you look at a jet engine and look at the requirements of a jet engine, if you put it as a jet engine, what are the requirements? Requirements is high temperature strength. Second is low diffusivity. Third is good thermal stability. Stability of the phases, what I mean is, that means the phase which has a high temperature strength should be stable up to high temperatures. Why this is very important here is because there is a phase transition that is possible here. Alpha goes to beta at high temperatures, 882 for a pure titanium. So if alpha transforms to beta during the service, then definitely you lose whatever advantage that you have as a high temperature strength. So because beta has a low has a high diffusivity, so low creep resistance than alpha. So if alpha transforms to beta during service, you don't want that to happen. So that's why you want the transition temperature from alpha to beta to be as high as possible. That can be achieved by adding some alloying elements. Like in steels, we add what are called alpha stabilizers and gamma stabilizers, isn't it? So similarly here, one can add what are called alpha stabilizers and beta stabilizers. And people have generally observed that if the E by A ratio is less than 4 for any element, all those elements stabilize alpha. If the E by A is more than 4, they stabilize beta, and if it is equal to 4, they are more or less neutral. So if you want to have alpha, so you add all those elements which have a low E by A ratio. That means if you want to use titanium based alloy for engines, you add all those elements which have a lower E by A ratio, so that you stabilize alpha. And once you stabilize alpha, then beta transformation from alpha to beta transformation does not occur so easily. So the transformation temperature can be raised. For example, you see in steels, when you add carbon to the iron, the higher the carbon that you add, the A3 goes down and the A4 goes up. That means the austenite stability range increases. Why? Because carbon stabilizes austenite, isn't it? So whenever you add an element which stabilizes a particular structure, its phase field enhances in that phase diagram. If you look at carefully iron carbon diagram, with increasing carbon, that from 910 the A3 temperature keeps on coming down to 723 at 0.83, 0.8 degrees, 0.8% carbon. Similarly, A4 temperature goes up. A4 temperature is the temperature where the gamma transforms to delta. That temperature also goes up. So you can have a much wider phase field. So exactly similarly, people have added various elements, and when you add various elements, you get various types of phase diagrams. These are some of the phase diagrams that you get. When you add alpha stabilizers, one possible type of phase diagram is this. You have an isomorphous, liquid transforms to beta, and again beta transforms to alpha, and you have a single phase alpha for the whole composition range from one end to the other end, and that you get when you add elements such as zirconium and hafnium. Zirconium and hafnium are isomorphous with titanium, where their crystal structures are exactly similar and the atomic sizes are similar, they satisfy all the Hume-Rodher rules, so you get isomorphous phase diagrams. And if you add other elements such as aluminum, gallium, indium, this kind of elements, and also what are called the interstitial elements such as oxygen, carbon, nitrogen, this kind of interstitial elements, they also stabilize alpha. And when you add this kind of elements, you get a different type of phase diagram where alpha is stabilized. How do you know alpha is stabilized from this phase diagram? We can see that alpha to beta transition temperature, which is given by this line, is going up with increasing amount of the stabilizer, and this temperature also is going up. That means the alpha transforms to beta at a higher temperature when you add an element which stabilizes alpha. And so one has to look at these two temperatures, which are called alpha beta transist temperature, and at when you do not add any element, this is equal to 882 for pure titanium, and when you add an element, it increases beyond, and that is what is an alpha stabilizer. And what are beta stabilizers? You can come here. Beta stabilizers, some of them are like this: molybdenum, vanadium, niobium. Have you seen any phase diagram like this in iron based alloys, steels? Exactly similar phase diagram. There is one or two elements which give you like that. When you add an element to iron, you get exactly similar phase diagram. What is that? Manganese, nickel, which are austenite stabilizers. There the high temperature phase is not beta, it is a gamma. So if you add some amount of, in fact if you add more than 8%, that is what is austenitic stainless steel. When you add more than 8% of nickel, you have single phase gamma at room temperature. That is why austenitic stainless steel is austenite even at room temperature. You are bringing down the temperature of A3 up to room temperature. This is nothing but the A3 temperature for you in the steels. Okay. So you are bringing down the A3 temperature to room temperature by just adding 8% of nickel, and similarly some amount of manganese. Nickel and manganese are gamma stabilizers there. So similarly here beta stabilizers can be added, where the beta to alpha transition temperature can be brought down. Here in case of alpha stabilizer, the transition temperature is increasing. In the case of beta stabilizer, the transition temperature is decreasing, and you get elements such as molybdenum, vanadium, niobium give you this kind of phase diagram, where you have completely beta beyond a certain amount of molybdenum or vanadium or niobium. And you can see all these are BCC elements. We always know that when you add a BCC element, BCC's phase gets stabilized. This is a typical understanding of all of us. So that is why molybdenum, vanadium, niobium, they all stabilize that. And coming to other type of elements, other transition metals, They do not give this much stability, but definitely they give you a stable regime. Again you can see the transition temperature here decreases. Here also the transition temperature is decreasing, and you get eutectoid type of phase diagrams. And in fact this type of phase diagrams are more useful than this type of phase diagram. If you have this type of phase diagram, beyond certain amount you cannot do any heat treatment. These are all non-heat treatable alloys. Only below this you can do heat treatment. And there also you can have beta to alpha transition, nothing more than that. Whereas if you have a eutectoid transformation, then one can have beta giving you alpha plus some other second phase, and one can control the morphology of this. One can have lamellar, one can have whatever type of possibilities like pearlite, bainite, all kind of microstructures possible whenever you have a eutectoid type of a phase diagram. That is why all these elements are very useful to give you eutectoid transformation. But there is certain limitation as far as the addition of these elements are concerned, because when you add too much of element, some intermetallics come into picture. One such thing is with alpha stabilizers. When you add too much of alpha stabilizers, for example, there is something called alpha equivalent. If you remember, a similar equivalent we hear in iron carbon alloys, carbon equivalent in case of cast irons. When you have a carbon equivalent more than some amount, you get a grey cast iron. If the carbon equivalent is less, you get a white cast iron, because carbon is a graphite stabilizer there, isn't it? So whenever you add a high amount of carbon, silicon is also a graphite stabilizer. So because of that, silicon also comes into the carbon equivalent as a positive quantity. But other elements which take out carbon and form intermetallics such as chromium, molybdenum, vanadium, all those things go as negative values into the carbon equivalent, if you remember your cast iron spot. So similarly here there are what are called alpha equivalents. So aluminum is an alpha stabilizer, tin is an alpha stabilizer, zirconium is an alpha stabilizer, all these alpha stabilizers plus the interstitial elements such as oxygen, carbon, nitrogen, all of them come into this. And if this carbon equivalent, alpha equivalent, sorry, I should not call carbon equivalent. So if the alpha equivalent is less than 9%, you get alpha. If it is more, then you end up in a compound called Ti3Al. And Ti3Al is an ordered compound with a DO19 type of structure, which is basically a hexagonal type of structure and a high melting compound. So, but the only problem is its formability is poor. So if you want more formability into your alloy, do not add large quantities of these alloying elements to end up in this Ti3Al. But at the same time, an intermetallic with a high melting point and an ordered structure, if it is present in a matrix of metal, you will definitely get much higher strength. So that's why you can think of an alpha matrix with particles of Ta3Al to get you much higher strength. And this situation is exactly similar to our nickel based superalloys, where you have gamma gamma prime, we say, where you have an FCC matrix which is nickel based solid solution, and what is the precipitate there? Ni3Al. Ni3Al is an ordered FCC L12 structure, and that gives you much higher strength. And a similar microstructure we have seen in aluminum based alloys. What is that? Exactly similar structure we have seen in aluminum alloys. I have taught you in the last 2-3 classes. Aluminum Al3 Li. You have an aluminum matrix, Al3 Li, which is again an ordered FCC structure. So you have an FCC matrix and an ordered FCC particles in a matrix, and that also gives you a good formability and at the same time good ductility. Another possibility is what I told you is the another alloy which is again a similar situation with an FCC matrix and an ordered FCC particles. What is that? Again aluminum base. Al3Ti, ordered Al3Ti, which is a L12 structure. If we can convert the DO22 structure or DO21 structure of Al3Ta and Al3Zr into an L12 structure from the tetragonal to cubic structure, which we have shown examples of it, again you have an ordered structure of a cubic structure, ordered particles in a disordered cubic matrix. So all these are examples which are similar to the gamma gamma prime type of nickel based superalloys, and you can get much higher strength. Only thing is here, because the hexagonal matrix is there and ordered hexagonal particles, the formability here is not very high. One has to remember that, but one can use this. And when we think of the alloys that are possible, there are alpha alloys which are basically stabilized by alpha stabilizers, aluminum and tin. 5% aluminum, 2.5% tin is a typical example of an alpha alloy, and beta alloys which are stabilized by beta stabilizing elements such as vanadium, chromium, and you also add a small amount of aluminum. Why do we add this? Is because most of the beta stabilizers, interestingly if you look at it, they are all having high densities. So because of which beta alloys are heavier alloys when compared to alpha alloys. Alpha is stabilized by aluminum, interstitial elements, tin, this kind of elements, okay, because of which the alpha alloys are low dense alloys. So because we are all adding elements which have a lower density, so the overall alloy is having a low density. So that's why these are the alloys which are for high temperature applications and at the same time less density, whereas the beta alloys, because we are adding elements which have high densities, so because of which the overall alloy becomes dense. Then we can have alpha beta alloys where you can have a combination of alpha stabilizer and a beta stabilizer. The most popular alloy is titanium 6 aluminum 4 vanadium, but there are limitations again. The alpha beta alloys cannot be used for high temperature applications, one has to control that. And in these alpha beta alloys, one can control the properties by controlling the microstructure. We will talk about this in the next class, how to control the microstructure to control the properties in these alloys.